Dear colleagues, ladies and gentlemen, I'm very sorry that I cannot attend the meeting this year in person, but I'm very pleased that I can present some of our research work, and I very much hope that next time I can join you again in beautiful Greece. Today, I will talk about premature cardiometabolic aging in space, learning from astronauts for patients with cardiovascular disease. Now, cardiovascular aging in space has several facets. So one of the conditions that we commonly encounter in space or following space travel is cardiovascular deconditioning and orthostatic intolerance, which on Earth usually occurs as you age. And orthostatic intolerance can be a major problem. Now, just imagine that an astronaut gets out of a spacecraft on another celestial body and experiences syncope and falls, which could be life-threatening. Another issue that we have been interested in is thromboembolic disease. I showed during the last meeting that with changes in G-forces, platelets can be activated, and that surprisingly, in perfectly healthy astronauts, thrombosis of the neck veins can occur spontaneously. And lastly, a concern that we haven't really had a hold on is early vascular aging and atherosclerosis. And I will tell you why there are concerns that people in space could be exposed to this increased risk. Now today, I would like to introduce our research approach a little bit. So I will show you how we conduct in space to learn more about health effects of space, of the space environment. I will talk about terrestrial models that are required because we cannot do everything in space that we would like to do in space in terms of medical research. And lastly, I will tell you how we try to apply our technologies and our knowledge that we gain in space medicine for patients on Earth. Now, why are there specific health risks in space that we may not encounter on Earth? There's a term called the space exposome, and I would refer you to a recent review paper in Aging Research Reviews that was published, and the lead author was Miriam Capri. And in addition to the cardiovascular risk factors that we know from Earth, that there are additional risk factors that are specific for space. Most obviously, microgravity. So people are not exposed to regular weight, to regular gravity. They are in weightlessness conditions, which unloads the cardiovascular system, predisposes to cardiovascular deconditioning and orthostatic intolerance. There are abnormal circadian rhythms. For the normal 24-hour, the rhythm is not present in space. There's also an exposure to galactic cosmic rays and to solar energetic particles, which can damage cells. And you may have heard that, for example, following atomic bomb explosions in Japan, there was an increased risk of cardiovascular disease many years after the exposure. It's also been shown that after exposure to radiation therapy, the risk for cardiovascular disease can increase. And there are many other stressors. Some of them are specific for space, but others can also occur on Earth, like confinement, stressful work overload, social stressors, and so on. Now, first, I would like to talk about radiation as one of the risk factors that can affect health, that can also affect vascular health. And here is data from our biophysics department, and our colleagues measured radiation on Earth, on the International Space Station, on the Moon, and on the Mars. And first of all, you have to recognize that the type of radiation exposure is vastly different in space than on Earth. So in space, people are exposed to high energy particles that cannot be shielded. But when you look at the radiation dose, you can easily see that compared with Earth, radiation exposure is approximately 300-fold increased on the International Space Station and almost 600-fold increased on the moon surface, a little bit less on the Mars, also approximately 300-fold. And so when a person is in space, for example, the radiation dose that would be tolerated in occupational settings would probably be reached after 1 or after 2 years. Now, the problem with these measurements is that in order to understand the health risks that are associated with radiation exposure, you have to know exactly the organ doses, so how much reaches specific organs. And to learn more about that, we conducted the so-called MAR experiment. The MAR experiment was conducted during the Artemis 1 mission. You may have heard that the Americans, NASA, are planning to return to the moon, and the missions are called the Artemis missions. And the first mission of this Artemis program started last year, and it was a space capsule that is built for human beings, but in the first flight it was not manned. So it was an unmanned mission, and we had the great privilege to fly 2 phantoms, so 2 anthropomorphic female phantoms, which are shown here. They were called Helga and Sohar, with this mission on an astronaut seat. And these anthropomorphic phantoms do not only have the shape of the human body, they also have the radiation density of the human body, so that you can exactly determine radiation doses in specific organs. And so these phantoms were equipped with several thousand passive dosimeters to assess the overall radiation dose in this mission. And then with active dosimeters, these are these electric devices with cables that you can see on the slide. And these dosimeters can be used to determine changes in radiation exposure over time. And so one of the phantoms, Zohar, here on the right-hand side, was also equipped with a novel radiation protection vest that was developed by an Israeli company. And so the idea was to first determine the radiation dose in the female body, and then to determine what types of radiation and how much of that could be shielded with this novel radiation vest. Here are just some impressions. So that's the team in Houston at the Johnson Space Center. Both phantoms were mounted, and in the back you can see the team that was involved. So people from Stemrad, so the company that made the vest, from Lockheed Martin, from NASA, and then our people from the German Aerospace Center. And so the phantoms were ready to go. Here's the vehicle assembly building where the rockets are assembled. So it's a huge building. You have to see it when you ever have a chance to travel to Johnson Space Center. And on top of the SLS rocket, the moon rocket, there's the Orion spacecraft, so the space capsule. And in the space capsule, the 2 phantoms were mounted. And after a long wait, because usually many of the space missions get delayed because of technical issues or weather, but eventually the mission started successfully and they were flown to space. They traveled all around the moon, and in fact, this spacecraft there's never been a human-rated spacecraft that was so far away from Earth. They traveled around the moon and arrived safely in the Pacific Ocean, where the capsule landed. The capsule was taken overland again to the Johnson Space Center in Florida, and both phantoms arrived safely. And now our colleagues are analyzing the dosimeters and will know more about the radiation exposure. And we are really interested in the risks that could be associated with this exposure and whether the radiation protection vest is helpful. And we are not only interested, of course, in cardiovascular health, we are also interested in potential cancer risks and others. So that's an example of how we conduct research in space. But I have to say that research studies in space, and we also conduct studies with human beings in space, are very tedious. We have very few subjects that we can study over time, and our methodologies are extremely limited. Even a blood sample or an electrocardiogram in space is difficult to obtain, and more advanced medical technologies may not be available at all. So in order to learn more about space and in order to develop countermeasures, which is another word for preventive medicine, we have to have models on Earth that simulate certain aspects of space travel. And we are very fortunate to have the NWAP facility on our campus in Cologne in Germany, right next to our main institute building. The NWAP, the name of the building comes from environmental habitat, so a building where you can simulate relevant environmental conditions and then conduct detailed human phenotyping studies. And we apply our capabilities to develop and test countermeasures for aerospace medicine. But we also apply our opportunities for disease, to better understand disease mechanisms in patients on Earth, or for pharmacological studies in human beings. One of the models for space that we apply are so-called head-down tilt bed rest studies. So the idea is that you put human beings in bed, which causes deconditioning, much like the changes you observe in human physiology in space. So you unload the body, you lose body mass, you lose bone mass, you lose muscle mass, you lose cardiovascular fitness. But in addition, the whole bed is tilted down by 6 degrees. This causes fluid redistribution towards the head, much like the changes that we observe in weightlessness. And typically, these studies have a duration of 30 or 60 days, depending on the physiological readouts we are interested in. And you can then apply the model to test potential countermeasures. So on the left-hand side, you see a subject in one of our bed rest studies in the head-down tilt position. And on the right-hand side, you see one of the countermeasures that we are testing. And these are impressions from a study that we conducted together with ESA and NASA in our center, the so-called EGBRISA study, where we tested centrifugation, which elicits artificial gravity as a potential countermeasure for bed rest. And so what we do what we did in the study, we had a control group without a countermeasure, and then two groups who were put on the centrifuge for 30 minutes each day. We were centrifuged with 1G at the heart level for 30 minutes per day. One group continuously and one group discontinuously, 6 times 5 minutes. And so the idea was to test artificial gravity as a potential multi-purpose countermeasure. So we had the hope that in addition to preventing cardiovascular deconditioning, we could maintain orthostatic tolerance. We could perhaps help to maintain bone mass and attenuate the fluid shifts towards the head that you observe in bed rest and in weightlessness. Just to show you one of the readouts in this study, so before and after the study, we measured orthostatic tolerance on a tilt table. This tilt table is shown here on the left-hand side. So that's a tilt table. We put people in the upright position, and in addition, and you may have a hard time to see this, we apply lower body negative pressure. So first, we simply tilt people up. Then we add lower body negative pressure and increase lower body negative pressure until subjects cannot maintain the upright position anymore. So until either they have pre-syncopal symptoms or the blood pressure falls to low levels. This is shown here on the right side. So these are heart rate and continuous finger blood pressure measurements. You can see immediately when The person was tilted up, heart rate increased, blood pressure was maintained, then lower body negative pressure, minus 10 millimeter mercury, and then minus 20 millimeter mercury were added, and eventually blood pressure decreased, and the tilt test was aborted. And what we measure is the time to presyncope, which is a well-reproducible measure for orthostatic tolerance. And we do this before the study and after the study, and in the control group, and in patients and in subjects who were exposed to artificial gravity. And that's the Kaplan-Meier curve. It shows orthostatic tolerance before and after bed rest. And so the red curve shows the orthostatic tolerance before bed rest. The left curve shows how long it took to experience presyncope after bed rest. And obviously, there was a massive reduction in orthostatic tolerance in the control group following 60 days bed rest. And here on the right-hand side, this shows the change in orthostatic tolerance, first in the control group, the black bar, in the continuous artificial gravity group, and in the intermittent artificial gravity group. And you can see that the worsening in orthostatic tolerance was substantially attenuated in the group exposed to artificial gravity. So at least for orthostatic tolerance, 30 minutes per day, artificial gravity was an effective countermeasure. However, several of the other outcomes that we measured, like bone mass or changes in fluid overload in the head, did not improve. So artificial gravity alone is probably not sufficient. And in future studies, we will combine centrifugation with other countermeasures like physical exercise, for example. But this is just to show you how we apply terrestrial models to conduct research for space. Since we have all these all this equipment, we can also apply this for people on Earth. And one of the environmental factors that is important for people in space, for people in aeronautics, but also for our patients on Earth is environmental oxygen. Just to give you an idea what the relevance of oxygen in space, well, on the International Space Station, conditions are actually very similar to conditions on Earth. For example, so there's no normal atmospheric pressure and approximately 21% oxygen content, a slightly increased carbon dioxide, but otherwise very similar to Earth. In other spacecrafts in the past, these conditions were quite different, ranging from 100% oxygen to reduced pressure and slightly increased oxygen. So there has been a wide range. But when astronauts leave a spacecraft, which is shown here, a so-called extravehicular activity, or EVA, the atmospheric conditions have to be changed dramatically for the simple reason that pressure has to be much lower in the spacesuit because it would otherwise become way too stiff. You know, like a tire on your bicycle or on your car. When you increase pressure, it becomes harder and harder. And so there's only 1/3 of atmospheric pressure approximately in such a suit. And so oxygen has to be increased. And so it is increased to 100%. And so that's an example of the extreme atmospheric conditions that astronauts encounter. So we have pressure chambers or chambers where we can manipulate oxygen content or carbon dioxide content under normal conditions. And we apply this again for aerospace, but also for medical studies for people on Earth. And that's now the third topic and the last topic. One example that we have really been interested in is the role of environmental oxygen in cardiac regeneration. And this research program was inspired by a recent study by colleagues in the United States from UT Southwestern, Hisham Sadiq's group, and we closely collaborate. What they did is they found out that one of the factors that regulates the ability of mammals to regrow cardiac tissue is oxygen. So So when a newborn mouse, which leaves the hypoxic conditions of the mother, has the ability to regrow the heart just a few days or weeks after birth, this regenerative capacity is lost. And this is due to environmental oxygen. Now, remarkably, when you take an adult mouse after myocardial infarction and you expose this mouse to very low oxygen levels for 2 weeks, which is shown on the left side. So mice were acclimatized to hypoxic conditions and then stayed in 7% oxygen for 2 weeks and then recovered. And so in this hypoxic condition, which resembles almost a trip to Mount Everest, the regenerative capacity of the heart is restarted. And the authors showed that not only does the heart regrow, ejection fraction gets better after hypoxia exposure, and the mice are better off. Now the problem is when translating these findings to human beings, that most people said it is impossible to do such a study in human beings, so we will never know whether the same mechanism also exists in human beings. Can we switch on cardiac regeneration? And we felt that we should try to do that. And so together with our colleagues at UT Southwestern, we first did a pilot study to mountaineers, and the photo shows these two mountaineers. That's Ralf Dumowitz, one of the most famous German mountaineers, and his partner. And they've been to a 7,000 and 8,000 meter high mountain. And so we exposed these volunteers to conditions almost similar to the conditions in the mouse experiment. So they were acclimatized, then they stayed at oxygen levels resembling almost 7,000 meters altitude for 2 weeks. And you can see that our colleagues, so in the red t-shirt, that's Professor Tank, who was the principal investigator of the study. So the people who worked there had to wear oxygen masks because they were not acclimatized. And so we tested the tolerability and safety of exposing people to such severe hypoxia for a long duration in mountaineers, because they are experienced in hypoxia. And we learned a lot. First of all, the exposure was tolerated. On the left-hand side, you can see estimated right ventricular pressures. So when you expose people to severe hypoxia, a common phenomenon is pulmonary hypertension. And over time, the pulmonary hypertension actually improved. And when they were exposed to hypoxia, to normoxia again, pulmonary hypertension was completely reversed. We also learned many other things. For example, we learned that we can reproduce the reduction in skeletal muscle mass that has been described in mountaineers with long duration sojourns to high altitude. But the most important finding was it was safe and reasonably well tolerated. So the next step was to conduct such a study in actual patients. And so we conducted the first feasibility and safety study in 4 highly selected patients following acute myocardial infarction. So they were fully revascularized, had a myocardial scar, and they had one thing in common: they were all athletes. So one of them was a triathlete, one was a mountaineer, one was a mountain biker, and so on. So they were extremely fit, even though they had a myocardial infarction. And so in this pilot study, we exposed them to hypoxia, but much shorter. So they stayed with us for a bit more than 20 days, and we exposed them to oxygen resembling the conditions in approximately 4,500 meters altitude. We were interested in safety. So, for example, we did not observe any increase in high sensitive troponin. Left ventricular ejection fraction was actually improved after exposure to hypoxia, and we saw a reduction in NT-proBNP. We conducted some mechanistic studies. On the right side is a pretty complicated experiment. So apparently the effect of hypoxia on myocardial regeneration is mediated by the so-called DNA damage response. And so we conducted ex vivo studies. So we obtained blood samples from our study participants in normoxia, in hypoxia, and then after recovery. And we exposed wild blood cells ex vivo to radiation and measured how rapidly DNA was repaired. And interestingly, we saw a marked difference. So in hypoxic, in normoxia, there was a lot more DNA damage compared with hypoxic conditions. So it could at least indicate that the proposed mechanism that contributes to myocardial infarction was actually engaged by hypoxia. Of course, that's not proof that the same occurs in the heart. And so now the next study, the last study that we conducted very recently, and we are still analyzing the samples or the results, is a study where we actually exposed patients for 2 weeks, so like the mice experiments, to hypoxia. And you can see again, our people working in the experiment had to wear oxygen masks, and these are 2 patients following myocardial infarction. You may see in the back at the wall, they are under hypoxic conditions resembling an altitude of more than 6,000 meters. And they are exercising. And before and after this study, we conducted PET MRIs of the heart. And again, we are still analyzing the samples. I hope that I can show you the result next year. But I think whatever we find is interesting in case we find that the heart starts to regenerate after profound hypoxia exposure. That's important. It doesn't mean that in the future we will send all our patients to Mount Everest, but it would prove that the mechanism is also existent in human beings and that we can perhaps find other ways to activate this mechanism. And with this, I would like to conclude and thank you very much for your attention.